Hi, everyone. My name is Ilya. I'm the tech lead of the RBD team. I will be giving an RBD update, going in a little bit more detail into the features that shipped in Pacific and also covering what to expect in QUIESCE. So the first specific that I want to cover is instant import. The image live migration feature that was introduced in Nautilus for use cases such as moving the image from a replicated pool to an erasure-coded pool with minimal downtime has been extended to support external data sources. And in effect, it can now be used as an alternative to RBD import command. The advantage is that the image becomes available for use as soon as the migration is prepared, which is basically instantaneous because it just creates an empty image and makes a record of the data source and the data source format in the image header. Supported data sources include file, both local and remote, served over HTTP or HTTPS, and an object in any Amazon S3 compatible object store. And that file or object has to be in either RAW or QCOW or QCOW2 format. But note that the advanced QCOW and QCOW2 features such as compression, encryption, cloning, here referred to as backing file, external data file, and some others are not supported in Pacific. And so once the link to the data source is set up, the image, even though it is still empty, can be opened as if it was already fully imported. A read on an initialized area would be redirected to the data source. A write on an initialized area would check if it overlaps with something in the data source, with something initialized in the data source. And if so, trigger a so-called deep copy up, and that would pull the data into the image that is being imported. Of course, one thing to keep in mind is potentially high latency if your data source is remote, because the image can be literally anywhere. And here are some examples of how you might import a QCOW2 image from a remote HTTP server. The first one is the most straightforward and also the slowest one. We just fetch the file, convert from QCOW format to RAW in a separate step, and then call RBD import command. In the second example, we take advantage of the QEMU image capability to read directly from the HTTP server and write directly to the Redis cluster. It does not use extra space, and it is faster because the conversion from QCOW to RAW happens in parallel with importing. But you still need to wait for the import to finish before you can open and use the image. In the third example, we do a migration-based instant import. So the image can be opened and used right after RBD migration prepare command, so right after the first step. And then RBD migration execute command can be invoked at any time to hydrate or populate the image by forcing those deep copy ups to happen in the background. And this can happen while the image is being actively used. And finally, once the image is fully imported, RBD migration commit command can be used to disassociate it from the data source. And at that point, the migration is finished. The second feature, definitely worth highlighting, even though it did not get completed in Pacific, is built-in encryption. The need for encrypting data on the client at image granularity with per image keys comes up more and more, and not just from financial or other similarly regulated industries, but also from small regular users as well. Layering QEMU encryption or DMCrypt on top of librd suffers from a major limitation that a copy on write clone must be encrypted with the same key as its parent. If you don't want that, you basically end up having to abandon thin provision clones in favor of thick copies. And to solve that, support for LUKS-based encryption has been incorporated within librd. We use a standard AES cipher in XTS mode for full disk encryption. This is more or less the state of the art in the full disk encryption technology right now. And this is what LUKS defaults to on with regular devices. And as far as the implementation, there are no reinvented wheels here, at least not yet. We use libcrypt setup for working with the LUKS header and the OpenSSL library for the actual encryption. Both LUKS1 and LUKS2 formats are supported. And for LUKS2, we set the sector size to 4 kilobytes for better performance across the board. But this can hurt some workloads because any writes smaller than or not aligned to 4 kilobytes will incur an expensive read modified write cycle. So if you have a 512 byte workload, you might want to stick to LUKS1. Clone images inherent parent encryption profile and key. And unfortunately, only flat, that is non-cloned images, can be encryption formatted in PACIFIC. This means that the limitation that I just mentioned, is still there in PACIFIC, but it would be resolved in QUIESCE. And here is an example of encryption formatting an image and mapping it with RBD NBD. Encryption format command generates the LUKS header. Generates a LUKS master key, adds the supplied passphrase to key slot 0, and then writes out the LUKS header. And because it is a standard LUKS format, a standard LUKS header, Crypt setup tool can be used to add additional passphrases or perform any other maintenance operations that you would typically do on a LUKS volume. And another cool consequence of using LUKS is that as long as the image is not an encryption formatted clone, which is coming in QUIESCE, its layout is understood, for example, by DMCrypt. And so you can see an example here of mapping the same image with kernel RBD, which doesn't know anything about librd encryption. And we just open the LUKS container on it, and it works. Next up is two performance items. The first one is a vast improvement in small I/O performance, thanks to work that started in Octopus and was completed in PACIFIC. A single librd client often topped out somewhere between 20 and 30,000 4 kilobyte IOPS, mainly due to issues with the internal threading architecture. There were several context switches per I/O, and that is not counting the actual processing on the OSD, and that really matters at flash speeds. A single so-called finisher thread handling the callback queue in libradis did not help matters either. And so to address that, librd I/O path has been rewritten in PACIFIC, and it now sits on top of the new NeoRadius API that landed early in the PACIFIC cycle. It provides a pool of boost as I/O context reactive threads, and that allowed us to kill numerous ad hoc, one-off threads and thread pools within LibRBD and some in LibRadis. And this resulted in generally lower latency and up to 3 times increase in IOPS for some benchmarks in all-flash clusters. Going forward, the switch to an asynchronous reactor model may also allow LibRBD and LibRadis to tighter integrate with SPDK. In an ideal world, we would have a single reactor handling everything from SPDK or maybe even QEMU in the very far future, all the way through LibRBD and down to the, all the way through the objector and down to the messenger layer in LibRadis. That would be really cool and eliminate lots of bottlenecks. The second performance item is client-side persistent write-back cache. For many different use cases and workloads, setting up a persistent write-back cache on the client is a sensible choice and an acceptable trade-off. But the problem with doing it today is that layering something like DM cache on top of LibRBD is too risky because dirty cache blocks are flushed to the backing image out of order. This is done according to whatever cache policy, but none of the supported cache policies can implement in order flushing. And so with the current caching solutions, at least those that are widely used and easily available out of the box, you're sort of stuck at one of the two extremes. Either the cache is not write back and a synchronous write gets ACKed only when persisted in the cluster, which does not help the latency problem. Or a synchronous write is ACKed when persisted on the cache device, but the write back is not ordered, which leaves you with a backing image that is most likely corrupted from the file system or user application point of view, because it is essentially a mix of old blocks and new blocks, with old blocks potentially being really, really old for offsets that correspond to hotspots, which would be the file system journal, for example. So as soon as that is off, even by a couple of bytes, the file system is gone. So there is now a LibRBD plugin that implements a log-structured persistent write-back cache. The key here is the log aspect. A synchronous write gets ACKed to the user as soon as its log entry is persisted on the cache device, and dirty log entries are flushed to the backing image in order. As a result, the backing image is always point-in-time consistent, no matter what. And if the cache device is lost, you only lose a small bounded amount of updates, typically in the range of single-digit seconds or something like that. So the new cache comes in two flavors, one targeted at persistent memory devices and another for SSD devices. They share a common core, and the flushing logic, the I/O dispatch code, things like that, but they differ in on-disk format and in how the cache device is accessed. In the persistent memory mode, which is referred to as RWL, for historic reasons, the on-disk format takes advantage of byte addressability of persistent memory, and it is just very simple head and tail pointers in the pool root structure, a contiguous log entry table, and a contiguous data area. The SSD mode is more complicated. because updates are done in 4 kilobyte blocks. The log entry table is spread throughout the cache device in the form of a linked list. And there is a certain amount of coordination that needs to happen when the data is written and the log entry is committed and then the root is updated. So it is more involved. Additionally, everything gets zero padded to 4 kilobytes. So you should expect some cache space wastage if your writes are smaller than that. For accessing the cache device, the persistent memory mode uses a library from Intel's Persistent Memory Development Kit, and the SSD mode reuses Ceph's block device abstraction, which was written for BlueStore. And it's basically just libIO plus ODirect flag to bypass the host page cache. The latency improvement is dramatic, particularly for 99th percentile latencies. Some reports claim an almost 2 orders of magnitude reduction in small random write benchmarks. Latency reduction, I should say, which is huge for latency-sensitive workloads. But it currently has some rough edges. There is a cache reopen issue that affects both modes, the fix for which is expected in 16.2.5 stable release. And unfortunately, several stability and crash recovery issues that affect the SSD mode have been discovered after Pacific has shipped. Most of them already fixed in master, but a couple are still pending. And those fixes would be backported to future Pacific stable releases. Also, the user admin experience is definitely not where we want it to be. Observability is rudimentary at best, and the RBD status command is just outright misleading. So moving on to snapshot QS hooks. This is a couple of new RPC messages that allow coordinated snapshot creation. This comes up, for example, when creating scheduled mirror snapshots, which are initiated at the cluster level. So neither the hypervisor nor the user know anything about them. Since ensuring that the file system and possibly the user application checkpointed before taking a snapshot is always a good idea, by default, if any client fails to QS, the snapshot is not created. This behavior can be changed to ignore the error or skip the attempt to QS entirely. In Pacific, this has been wired up in RBD NBD. If --QS flag is supplied, the daemon would attempt to freeze the file system mounted on top of its device before taking a snapshot. And it is done from a simple shell script. You can specify your own script or an actual binary that, in addition to taking care of the file system, would also take care of your applications, ensuring application level consistency. And the goal here is to integrate this in KRBD and QEMU in the future. But at least in the latter case, it is somewhat challenging because QS ends up being initiated very low in the stack in the block device driver. And it is a bit of a layering violation because the information usually goes backwards in the stack. Quite a lot of work in the Pacific cycle has gone into the kernel client. Support for Messenger 2.1 protocol was added in kernel 5.11. It is controlled by the new ms_mode mapping option. And one caveat here is that currently there is no separate option for affecting only monitor connections. Also, the original Messenger 2 protocol from Nautilus is not and will not be implemented because it is deprecated and shouldn't be used. As a consequence, the kernel client would require a Messenger 2.1 enabled release of Nautilus and Octopus. And you can see the particular release versions on the slide. And of course, the legacy Messenger 1 protocol is still supported and will be for many years to come. In fact, it is still the default in the kernel. We should probably change that. Then there is support for replica reads that landed in kernel 5.8. This can be random OSD in the PG, or much more usefully, the OSD that is closest to the client. The closeness is determined by the specified crush location. And you can see an example. So if your client is in or close to data center DC1, you would provide that crush location string when mapping the image. And for the PGs that have an OSD located in DC1, the reads would generally go to that OSD. There are some corner cases, though, where a read cannot be served by the replica. And in that case, it is redirected to the primary OSD. And this is the reason for needing Octopus OSDs for this to work. Otherwise, you might run into data consistency issues. And also note that this feature only applies to replicated pools because there was some confusion in the community about this. The primary use case here is clusters that are stretched across data centers or cloud availability zones, where the primary OSD may be over the link that is not only higher latency, but also higher cost because inter-availability zone traffic in the cloud is usually much more expensive. And finally, there is support for compression hands that also landed in kernel 5.8. You can use this to enable compression on an image that resides in a pool with compression mode set to passive, or vice versa. You can disable compression if compression mode on the pool is set to aggressive. And this is useful if an image is, for example, encrypted, because there's no point in attempting to compress it. In Pacific, we have native Windows support. Ceph client code was ported to Windows, so we now have librbd.dll, libradus.dll, etc. The team at Cloudbase put together a WNBD kernel driver, Windows kernel driver, that provides a SCSI-like virtual block device. What it does today, it used to be a generic NBD client, but what it does today is it just passes I/O requests through to user space via device I/O control that is much more efficient. And in user space, RBD, WNBD, XZ daemon picks them up, transforms them, and calls into librbd. This is similar in concept to RBD NBD on Linux. This daemon can also run as a Windows service, and in fact, that's usually how it is run. And in that mode, it manages the mappings in a way that they're persisted across reboots with the information stored in the Windows registry. And it also provides proper boot dependency ordering. So RBD is really a first-class citizen on Windows now, because there's also support for Hyper-V and I believe other integrations. Alessandro covered this in a much greater detail in his Ceph on Windows talk earlier this month. The recording is already available, so I encourage you to take a look. And that's it for Pacific. So moving on to what is coming in Quincy. Starting with the usability and quality bucket, I already touched on encryption formatted copy on write clones and persistent write-back cache improvements. This is the continuation and hopefully the completion of the work started in Pacific. In particular, I want to highlight that it would be possible to have a clone encrypted with key A, of a clone encrypted with key B, of an unencrypted golden image. So that is, and that is thinly provisioned for copy and write, as you would expect from a regular RBD clone. Of course, it would not be compatible with standard dencrypt anymore. So there would be a flag or a magic string modified to prevent the lux container open example that I showed on the previous slide. Persistent write-back cache improvements, we already went there. Crash recovery testing is going to be vastly expanded, and we also need to make the status easy to get and easy to interpret, because tuning your cache, well, there aren't any tunables, but just seeing if it actually helps and how much is dirty, how much is clean, is very useful. Make RBD support manager module handle full clusters. Should allow removing images via the manager command interface when the cluster is full. This does not work today. The manager just hangs and not necessarily inside of the RBD support module. So this is a wider issue that spans outside of RBD. Replace RBD map script with systemd unit generator. This would generate a systemd unit per device, allowing other units to depend on it, and making systemd handle file system mounts and unmounts, including fancy things such as auto mounts that would be triggered by accessing the mount point. This also adds support for a couple of options such as no fail and similar, such that failed mappings don't fail the RBD map service, such as it is today, and a couple of other improvements in usability. Allow applying export diff incremental to export file. Currently, there's no way to do this without importing the image into the cluster, just to apply the incremental and export the result back. This is not a good user experience. So there will be a new option added to RBD import and RBD export commands, and this would support both full and incremental updates. And export-import of consistency groups is somewhat related. It should allow exporting and importing consistency groups in a manner similar to individual images. Again, both full export and export diff incrementals are meant to be supported. And this would introduce a new export file format for export files that can contain consistency groups. On the multi-site front, we're looking to improve mirroring monitoring and alerting. The goal is to come up with a unified mirroring metrics schema, at least across RBD and Cephfs, and expose this metrics to Prometheus. It should be done directly from RBD Mirror to avoid adding to the growing pile of manager performance and scalability issues. And it would also be more expressive because we can avoid the Ceph perf counters bridge. Expose snapshot-based mirroring in the dashboard is self-explanatory. Currently, only journal-based mirroring is supported, and this would probably tie into the improved monitoring item with perhaps fancier Grafana dashboards based on the exposed metrics. And snapshot-based mirroring of consistency groups should allow for mirror snapshotting consistency groups, and then mirroring those consistency group snapshots, again, similar to individual images, together with import-export of consistency groups item. Consistency groups would become really more of a first-class citizen in RBD, and in general, our import-export story would be or should be much better in Quincy. On the ecosystem front, the big ticket item is NVMe over Fabric's target gateway. At a high level, this is similar to the existing iSCSI gateway, but hopefully more performant and scalable. It would be based on the NVMe over Fabric's target provided by SPDK, and on the backend, use the SPDK RBD BDEV driver. One other advantage over iSCSI is that modern smart NICs, such as NVIDIA's Bluefield and others, can translate between NVMe and NVMe over Fabrics in hardware. And what it means is the RBD image can appear as a local direct attached NVMe disk, and this is completely transparent to the host. No hypervisor required, and it is independent of the operating system or kernel installed. And this would be useful for bare metal services and cloud providers, where the entire physical machine is landed to the customer. On the RBD NBD side, there is a kernel patch posted that makes it possible to implement safe reattach after RBD daemon is restarted. This would be used in the Kubernetes environment, where the RBD plugin pod or container, which is responsible for mapping the image, and which actually contains the RBD NBD daemon responsible for the image, can be restarted or upgraded at any time and we need a way to make that reattach safe. In the Kubernetes environment, it is relatively safe because the environment is highly constrained. But to expose this functionality wider, it is critical that there are some stopgaps in place, because currently this is one command away, one keystroke away from corrupting the image. The second RBD NVIDIA item is support for single daemon managing multiple images or devices. And the goal here is to reduce resource consumption, because currently we have a daemon per image, and that means a separate set of sockets, a separate libReDUS and libRBD instance, a separate set of credentials, and so on. To improve the volume density, which again comes up in Kubernetes environments, this is something that we're looking at for QUIESCE. And on the Windows support side, it would be nice to get a sustainable CI infrastructure set up, preferably upstream. Currently, there is a Jenkins job that runs, periodically runs on master, but we do not have any test suite coverage, and to add that, we need somewhere to pull from, and have that be up to date. And I think this is the last item. The QEMU block driver should receive a facelift in the upcoming 6.1 release of QEMU. The most important thing is probably RBD write zeros support, which is available since Nautilus, but the QEMU driver wasn't updated to take advantage of it. And this should allow us to close some holes in our sparseness story, because in some cases, when importing the image, if you remember that example with the fancy QEMU image command that I showed on one of the first slides, in some cases that actually breaks sparseness, and this should help resolve that. The second item is support for loading the encryption profile, so that the encryption formatted image can be opened. And I believe libvirt integration is planned as well, but that is blocked on this landing in QEMU first. And finally, there is a switch to QEMU coroutine infrastructure from the legacy asynchronous I/O emulation stuff that is currently in use. I think, yep, that's it. That's all I have. Happy to take questions.
Didn't see any questions in chat. If you have a question, feel free to unmute yourself and ask away. Well, it seems like you answered everybody's questions. Also, there were some issues with people being able to view the slides. That's because of Blue Jeans, so sorry about that.
hopefully it made it into the recording.
Yeah. Well, I was able to follow along, but Dan is saying he'll rewatch the recording. So, all
All
right.
right. Thanks for listening.
All right.
And
Thank
feel
you,
free to
Ilya.
ping me on IRC or by email. Thanks.